In this lecture, we look at rational functions. A rational function is a function which is the ratio of two polynomials. That is, the function is n of x divided by d of x, where n of x and d of x are polynomials. The numerators and denominators are polynomials. For example, here's a rational function. In this case, both the numerator and the denominator are quadratic polynomials. Consider the function g of x, which appeared in an earlier lecture. It was a bit complicated. It looked something like this. This function g is a rational function. We can put g into a fraction form as the ratio of two polynomials by finding a common denominator. The least common multiple of the denominators x plus 2 and 2x plus 1 is simply their product, x plus 2 times 2x plus 1. So we can write g of x as a fraction with this denominator if we multiply the first term by 1 in the form 2x plus 1 over 2x plus 1, multiply the second term by 1 in this form, and multiply the third term by 1 in this form. Then g of x has this expression, and if we combine the numerators, since there is now a common denominator, we get something like this. I have not simplified the numerator, but the denominator is now 2x plus 1 times x plus 2. We found a common denominator. The numerator in this polynomial, in this rational function, is a polynomial of degree 3. It could be expanded out, if we wanted to 2x cubed minus 3x squared minus 20x minus 15. And the denominator is a polynomial of degree 2. The algebra of mixed fractions, including the use of a common denominator, is an important tool when working with rational functions. Given a rational function f of x, which is the ratio of two polynomials, we are interested in the y and x intercepts. The y-intercept occurs where x is 0, and it's pretty easy to compute. Just plug in 0 to the numerator and 0 to the denominator. However, the x-intercepts occur where y is equal to 0, that is, where 0 is equal to n of x over d of x. As a first step to solving this equation, to finding the x-intercept, we may multiply both sides by the denominator and so concentrate on the zeros of the numerator, solving this equation. At this point, we have reduced the problem to finding the zeros of a polynomial, since n of x is a polynomial, and that's something we've done in previous lectures. For example, suppose h1 of x is this rational function, a quadratic divided by quadratic. The y-intercept is minus 2/3 0, since when I plug 0 into this function, I get 8 over minus 12, or minus 2/3. The x-intercepts occur where that numerator, x squared minus 6x plus 8 is equal to 0, and we can factor that, discovering that this is 0 when either x is 4 or x is 2. And so 4, 0 and 2, 0 are the x-intercepts. We do need to check that where the numerator is 0 does not conflict with the denominator possibly being 0. But here, when x is 4 and x is 2, the numerator is 0 and the denominator is not. So we're okay. Since rational functions have a denominator which is a polynomial, we must worry about the domain of the rational function. In particular, any real number which makes the denominator 0 cannot be in the domain. And that's all we have to think about when we ask about the domain of a rational function. The domain of a rational function is all the real numbers except those which make the denominator equal to 0. For example, the function we looked at before, if we factor the numerator and denominator, we get this, and it has domain minus infinity to minus 4, union minus 4 to 3, union 3 to infinity, simply since only x equals minus 4 and x equals 3 make the denominator 0, and those are the only things excluded now. The domain of a rational function is all the real numbers except those which make the denominator equal to 0. There are two types of zeros in the denominator. One common type of zero of the denominator is that which is not a zero of the numerator. In that case, the real number which makes the denominator 0 is a pole and gives in the graph a vertical asymptote. For example, looking at this function from before, we notice that the denominator has zeros at minus 4 and 3, so these elements are not in the domain. Since neither -4 or 3 is a 0 of the numerator, these values give poles for this function, and in the graph we will see vertical lines, x equals -4 and x equals 3, that are approached by the graph of this rational function. These vertical lines are asymptotes. In this case, we have vertical asymptotes with equations x equals -4 and x equals 3. Let's continue to look at this function. We factored the numerator and the denominator. The figure below graphs our function in blue and shows the asymptotes. The graph is in blue. The asymptotes, which are not part of the graph, are in red, and you can see the two vertical asymptotes, x equals -4 and x equals 3. If we change our function just slightly so that it is this rational function, where we factor the numerator and denominator in this way, something very different occurs. With this rational function, slightly different, the rational function is still undefined at x equals 4. You cannot plug x equals 4 into this rational function. If you attempt to plug in x equals 4, you get the fraction 0 over 0, which is undefined. But as long as x is not 4, we can cancel the term x minus 4 occurring in both the numerator and denominator and simplify it to just x minus 2 over x plus 3, as long as x is not 4. So as long as x is not 4, our rational function at the top of the page is exactly the rational function at the bottom of the page. In this case, there's a pole at x minus 3, like we would think, but there's a hole, or removable singularity, at x equals 4, where, just for that point, the function is undefined. There's no vertical asymptote at x equals 4. We simply have to skip over that point. We cannot define the function when x is 4. Here's a graph of the rational function x minus 2 over x plus 3. There's a graph of the rational function where we multiply numerator and denominator by x minus 4. The only difference is that now that we've multiplied by x minus 4 in top and bottom, we have a problem when x is 4, and we have to eliminate that possibility, so there's a hole there. That function has no holes, one red asymptote. This function looks just like it, except it has a hole where x is 4, because we cannot plug x is 4 into this one. No hole, hole. No hole, hole. When we looked at graphs of polynomials, we viewed the zeros of the polynomial as dividers or fences separating the regions of the x-axis from one another. Within a particular region between the zeros, the polynomial has a fixed sign, plus or minus, since changing sign requires crossing the x-axis. We use this idea to create the sign diagram of a polynomial, a useful tool to guide us in drawing the graph of the polynomial. Just as we did with polynomials, we can create a sign diagram for a rational function. In this case, we need both the zeros of the rational function and the vertical asymptotes as our dividers, as our fences between sign changes. To create a sign diagram of a rational function, list all the x values which give a 0 or a vertical asymptote, put them in order, then between these x values test the function to see if it's positive or negative, and indicate that by a plus sign or a minus sign. For example, looking at this function from before, it has a 0 at x equals 2 and a vertical asymptote at x equals minus 3. The sign diagram then represents the values of this function in the regions divided by x equals minus 3 and x equals 2. For the purpose of a sign diagram, the hole at x equals 4 is irrelevant, since it doesn't affect the sign of the rational function. To the left of x equals minus 3, you can check some values and see that h is positive. Between minus 3 and 1, my rational function is negative. And to the right of x equals 1, we can test some values and see that my function is positive. So the sign diagram looks like that. It has fences at minus 3 and 1, plus and minus signs between them. In the next presentation, we look at the end behavior of rational functions.